In this video, we're going to start some geometric proofs. Now, we've done algebraic proofs, so we know kind of the setup of what a proof is, but geometric proofs are going to take a lot of practice. And don't become frustrated with them at the beginning, because the only way to get better at these is through practice. So we're supposed to complete the proofs here. We're doing segment proofs in this. The entire section is on just line segments. And again, we're going to use that reference sheet that we completed a little bit earlier. Now, the first thing you need to know about a proof is you've got to go into it with a plan. Here's what we're given. We're given that E is the midpoint right here. That's the middle. So since that is the middle, that means that these two line segments have to be the same. So let's kind of go through and try to figure out a plan. How can we prove that 2 DEs is equal to 1 DF? Two of these line segments is equal to the whole line segment. Well, we know that if we were to add these two line segments, we get the whole thing. And since this is equal to this, then that means that, that means that this and this is the same. So that means that two of these would have to equal one of these. So we kind of have a plan. We kind of know what's going on here. So if you look at the statements, they've actually completed the statements for you. So that's we're going to kind of take baby steps here, and then by the end of this lesson, we're going to be doing these by ourselves. So first off, E is the midpoint. We start out with a given. We already knew that. And since E is the midpoint, we know that DE is equal to EF. And the reason we know that, if we go back to our definition of a midpoint, if M is the midpoint, then we know that this is true. So kind of the same thing in our section. By the definition of a midpoint, we know that DE would have to equal EF. Okay, in this next step, we're going to see a trick that we can use a good bit. What we've actually done, we've taken the previous statement, and we have simply added a DE to both sides. Let me underline the first one. And the reason we're going to do that is we know that eventually that this DE plus EF on the right side, DE plus EF, well, that's the whole line segment, and we know what we can replace that with. And then the DE plus DE on the left side, well, look what you're trying to prove. We want two DEs on that left side. Now, why is that even legal? If two things are equal, then as long as you're adding the same thing or equal things to both sides, that stays equal. That's the addition property of equality. Okay, in this next step, all we've done here is the DE plus DE we've turned into two DEs, and that's just simplification. We just simplified there. Okay, but now let's examine this right side. DE plus EF. Now we're trying to prove that two DEs, let's go back to up here, two DEs, which is what we have on the left side, is equal to the whole thing, DF. Well, this DE plus EF, we know DE plus EF, we're going to say that that's equal to the whole thing. And the reason for that, if we go back to our reference sheet, AB plus BC is equal to the whole thing. That's your segment addition postulate. So let's go back, and step number 5, the justification is segment addition postulate. And finally, now that we know that DE plus EF is equal to DF, then we can simply substitute that in right here, and two DEs would have to equal, instead of DE plus EF, would have to equal DF by substitution, and that is what we're trying to prove. Now, I do want to point out that in that last step that we could have also called that the transitive property. Substitution and transitive property of equalities are very similar to each other, and a lot of times those two concepts can be used interchangeably. Okay, number 2, we're given that KL is congruent to LN, so let me go ahead and mark it. And we're given that LM is also congruent to LN. Since I did one tick mark there, I'm going to do one tick mark there. So we want to prove that L is the midpoint of KM. Now notice that what I've done there, these two are congruent, which makes these two congruent. And again, that's going to be your transitive property. So since these two are congruent by the definition of midpoint, then we know that L has to be the midpoint because those two are congruent. So let's go through this proof. It shouldn't be a very long one. The first step is everything that you are given. Now, the next thing that we know, since KL is congruent to LN, and since LM is congruent to LN, then we know that they're equal in lengths. Now, the reason we're doing this is in these proofs, we have more properties of equality that we're going to work with instead of congruence. So what we do a lot of times is as soon as we see two things are congruent, we go ahead and say, well, since they are congruent, then that means they're equal in length, but so that we can use all of our properties of equality. So the reason that they are equal in length is because, again, we can go back to our right here to our definition of congruence. If they're congruent, that means they're equal in length. If they're equal in length, that means they're congruent. So that's the definition of congruence. And then in step 3, since KL is congruent to LN, LN is also congruent to LM. And again, we can use either one. That's the transitive or substitution property. I'm going to call it the transitive property of equality. And I'm going to start abbreviating property of equality with POE. And again, let me show you why you could use substitution there as well. Since LN is the same thing as LM, well, right here where you have LN, you can substitute LM. So that's the reason substitution or transitive property would work. Now, why is L the midpoint? Okay, now our last step said that KL and LM were the same size. Since those are the same size, then this has to be middle, because definition of a midpoint says if AM is equal to MB, then M is the midpoint. This is a biconditional because it is a definition, so you can use it forwards or you can use it backwards. So this implies this, so that would be true because of the definition of a midpoint. Okay, the next one, number 3. We're given that PQ and TQ are the same. Here is PQ and here is TQ. We're given those two are the same. We're given that UQ and QS is also the same. And we want to prove that PS, which is the distance from here to here, is the same as TU, which is the distance from here to here. And it does, again, it makes sense. If this has a length of 3, this is the same. If this has a length of 4, then this is the same. Well, both line segments would have lengths of 7. I just plugged in some numbers there just to show you, just to make a little bit more sense of this. So we know that we're going to have to use the segment addition postulate in here somewhere, because we know that 3 and 4 gives you 7, and also this 3 and 4 gives you 7. So let's see where we can go with this. So we kind of have a plan. We have our given in this first step. Now, since PQ and TQ are the same, notice what we did. Since they're congruent, then we're going to say they're equal in length because of that definition of congruence. And notice what we do in the next step. Is exactly what I said. We know that PQ and QS, which is this line segment and this line segment, when you put it together, it gives you PS. So what I'm doing, I'm listing everything that I know here. We know PQ and QS is PS, and TQ and QU is equal to TU. That'd be your segment addition postulate. Okay, so again, if we'll go back and look at what we want to prove now, PS and TU are the same. Look at what we just did. Here's PS and here's TU. That's the two things we're wanting to try to prove that are the same. Well, there's a few different ways we can do this, and this is one method that they're using, and I believe we use a different method here before this is over with. Since this is PS and this is TU, if we could somehow make these the same, then obviously PS and TU are the same, and that's what they're trying to do here, is they took this first statement, and they said, okay, PQ plus QS is PS. Well, since we know that PQ and TQ are the same, I could replace PQ with TQ. And then they're going to take this statement and do the same thing. They're going to say, okay, since I know that this is true, I could take out QU and I could put in QS. And notice what you now have. These two things are the same. And if PS and TU are equal to the same thing, then they must be equal to each other. So that's the method that they're going here. So let's see if we can figure out these statements that go along with this. So what we've done, again, we've took this first statement and we've rewrote it as this. We took out PQ and we put in TQ because they are the same thing. Now that one, we've got to be careful. That is definitely substitution because we took something out of this statement and we put something in its place that it's equal to. So therefore, we have the substitution property of equality. And then in step 5, we did the exact same thing except for with this one. So we kind of could have listed both of those in the same one. We took out QU and we put in QS because QU and QS is the exact same thing. Now notice they said UQ here. we understand it's a line segment. We can name it QU or UQ. That's the same line segment. So again, step number 5 is also the substitution property of equality. Now, to me, this is a tricky way of proving this, and this is, again, going to take a little bit of practice. But since PS and TU are both equal to the same thing, that's like A is equal to B, and B is also equal to C, so therefore these two must be equal to each other. That would be your transitive property. And then finally, in the last step, we can say what we were trying to prove, that PS is congruent to TU, because if they are equal, then by the definition of congruence, that means they're also congruent. Okay, the next one. Number 4. We're given that K is the midpoint of JL, which means these are the same. We're given that M is the midpoint of LN, which means those are the same. And then we're also given that JK and MN are the same. So wait a minute, if JK and MN are the same, that means I can put one tick mark here. And since this is the same as this one, that means I can put one tick mark here. So what are we trying to prove? That K, L, and LM are congruent, or the same as well. So we've kind of went through the steps there, and we kind of see how we're going to do that. We're probably going to have to use some substitution there, because let's see, these are the same, and these are the same, which means that these are the same. So probably a little bit of transitive property. So let's go through, and again, your first step is list everything that you know. That's going to be your given. But what else do you know from that given? Well, since K is the midpoint, we know that those will have to be the same. Since M is the midpoint, we know that those must be the same. So that's our step number 2. That's what we follow up with. And again, that's the definition, because the definition of a midpoint. Okay, step number 3, and this might throw some people off. They're like, well, how do we know that? Well, that's another part of our given. They've just listed it a little bit later. You don't have to list the entire given in the exact same step. That's fine. And the reason they did that is, okay, they did this part of the given, and that followed or led into this. And then you're going to say, okay, now we also know this is given. Well, what does that lead into? Okay, so let's see what we're given next. Step number 4. Step number 4 follows directly from step number 2. All we did was we used this fact. In step number 2, we said that because of the definition of a midpoint, we knew these were true. Well, notice this is the exact same thing, except for we've taken out JK and we replaced it with MN. So that was, again, we said when we were going through, okay, what do we know is true? Well, since we were given that those were true, then we could substitute that fact in, and that means that these must also be equal as well. So therefore, we used our substitution property there. Or again, you could say transitive, substitution or transitive there. And now that we know that, notice that in step 4 that both of these are now congruent to MN, or equal to MN. So since KL and LM are both equal to MN, then they must be equal to each other as well. And again, that is that same transitive property. Okay, next up, and they did this on purpose. We've got a little bit of a problem. We're trying to prove that KL and LM are congruent, but we've got them in the wrong order. We've got LM and then KL. Well, this next step says the exact same thing except for flipped around. So they're just showing you here, okay, why do we have that whole symmetric, reflexive, and some of these other properties that we have? If you have LM is equal to KL, well, we can flip those around. That's legal. And the reason we can flip those around is because of that symmetric property. If you go back and look at your symmetric property, now this is a symmetric property of congruence, which says if AB is congruent to CD, then CD is congruent to AB. Well, the symmetric property of equality says the same thing, except for we use it with equal signs instead of congruent symbols. And then finally, if they are equal in length, then they are congruent. That is the definition of congruence. And that is what we were trying to prove, that KL is congruent to LM. Okay, number 5. Okay, with number 5, you're going to start noticing some overlap, that a lot of these proofs look very similar. So that's the reason once you learn a method and once you learn how to prove these, a lot of that is going to start reoccurring. So we start out with our given, and we are given on number 5 that XY, which is here, is congruent to UV, and that TU is congruent to YZ. That's what we're given, and we're trying to prove that XZ and TV, the two line segments, the two whole line segments, are the same. So we're given that. So again, all of our properties and all this usually deals with equal lengths and all that. So we're going to change from congruent to equal by using our definition of congruence. Okay, and then let's think about, okay, well, if these are the same and these are the same, well, how are we going to prove that the whole thing is the same? Well, first off, we need to talk about that the whole thing is simply this line segment plus this line segment. And that's what you have in this next step. XY plus YZ is equal to the whole thing. TU plus UV is equal to the whole thing. That is your segment addition postulate. Again, that says, let me scroll down. The segment addition postulate says this little piece and this piece is equal to the whole piece. And then in this next step, then it starts looking very similar to one of our previous proofs. We're trying to prove ultimately that XZ and TV are the same. Well, if we can somehow prove that this and this is the same, then obviously XZ and TV would have to be the same. So that's going to be our next step, is we're going to try to make these the same. And the way that they did that here is they took out XY and they replaced it with UV. Well, why can we do that? Is because up here, XY and UV are the same. And then in the same step, now in a previous example, we did it in 2 steps. Here they're combining it all and just putting it in the same step because you're doing the same thing. You're taking out TU and putting in YZ. Why? Because TU and YZ are the same. Now, why can you do that? Why can you take something out and replace it with something that's equal to? It's because of the substitution property. You can substitute equal things. And again, why are we doing this? Look at the left sides now. UV plus YZ. And this is also UV plus YZ. Okay, so since they're both equal to UV plus YZ, then they must equal each other. So therefore, let's go ahead and write down number 4 is the substitution property. And then number 5, since they're both equal to the exact same thing, it doesn't matter the order, since they're both equal to the exact same thing, by the transitive property, then you can say they're equal to each other, which is what we have here. And finally, since they are equal to each other, notice that we're not trying to prove equality, we're trying to prove congruence. Since they're equal to each other, that means they're also congruent by the definition of congruence. Okay, number 6. Okay, number 6 is the exact same proof as the last one. The only difference is they have the 2 lines crossing instead of being next to each other. So exact same proof. However, we're going to work it a little bit different just to show you there's multiple ways of going through these steps. So first off, we're given that WY is equal to YZ and that XY is congruent to also VY. Okay, now in step number 2, we follow the exact same steps. Since they're congruent, then we know that they're equal in length, and that's your definition of congruence. And here's where this changes, just slightly. Now, it's worked very similar, but they've just changed just a little bit. Now, I don't like the order that we do this in. What we're going to do now, XY plus YZ is equal to XZ. Here's XY, here's YZ, that's equal to the whole thing. I would like to go ahead and put this right here. Why not go ahead and put them in the same steps? That VY and YW is also equal to VW. Both of those steps are going to be the segment addition postulate. Okay, now here's where it's a little bit different, and I kind of like the way they do it in this one rather than the previous ones. It makes more sense. What they're going to now do is they're going to take this XY plus YZ, which is equal to XZ. And since we know that XY is the same thing as VY, and we also know that YZ is the same thing as WY, they're going to replace XZ with VY, and they're going to replace YZ with YW because they're the same thing. Notice that the order is different. WY, YW is the same thing. So they're going to replace those two, and that's because of, again, this statement number 2. So that's just going to be simple substitution. But now look what we can do. We can combine statement 3 and statement 4. Okay, that since we know, not statement 3 and statement 4, statement 4 and 5. There we go. Look, they're both XZ and VW now. Since you replace these over here, they're now equal to identical things. And since they're equal to identical things, then they must be equal to each other. And that's going to be your transitive property. which pretty much finishes up the problem. Since they're equal to each other, we know that they're congruent to each other by the definition of congruence. Okay, the next one. Number 7. Okay, notice in this one that we're given some statements and some reasons. Again, we're taking baby steps. Now we're starting to mix it up with, okay, sometimes you'll have to give the reason. Sometimes you might have to give, well, what's true because of this. And this is not going to be too bad as long as we understand the plan, okay? In the given, we know that E is the midpoint. So that means that these are going to have to be the same. But we're also given that DE and EC are the same. So since EC is one tick mark, then DE is one tick mark. So that means by the transitive property, these would have to be the same. So that's your plan. So let's go ahead and jot that down. E is the midpoint. That was your given. Okay, since E is the midpoint, that means that these two have to be the same by that definition of a midpoint. We know that, again, that AE has to be the same length as EC. Okay, also in our given, notice, we are given that DE is the same length as EC. Okay, now since these are the same, AE is EC, DE is EC, then we can then say that AE and DE have to be the same. Because of, again, you can do it either way, transitive or substitution. And now that we know that AE and DE are the same, then that means that they must also be congruent. If they're the same, then they are congruent by the definition of congruence. But we have a problem. That's not what we were trying to prove. We're trying to prove that DE and AE are congruent, not AE and DE. We have them in the wrong order. So therefore, now you got to be careful. We're dealing with congruence now, not equality. And they did that early. I mean, we could have went ahead and flipped it here and said that DE and AE are the same, but they want you to remember that you also have a symmetric, a transitive, and a reflexive property of congruence. So therefore, why can we take AE and DE and flip them around now that they are congruent? That is because of the symmetric property, symmetric, and I'm going to write this out, symmetric property of congruence, not of equality anymore, the symmetric property of congruence, since you are dealing with congruent symbols. Okay, number 8. Okay, if you go back and look, number 8 is nearly identical to number 1, just backwards. Okay, we're given that RS is equal to 1/2 times RT, or half of RT. So if this is equal to half of the whole thing, then we want to prove that then S is the midpoint. So kind of the same thing, like I said, with number 1, just backwards. So we're given that RS is equal to half of RT. Now, one thing that is different is on the first one, we weren't dealing with the fraction. But notice what step number 2 does. It says that 2 RS's is equal to RT. So how can we manipulate this to get that? Well, what we're going to do is do a little bit of algebra here. We're going to multiply both sides by 2. 2 times this, and then when you multiply 2 times a half, it gets rid of it. So that's, like I said, that's a little bit of basic algebra. So you now have 2 RS is equal to RT. And the reason we did that, we multiplied both sides by 2. And that is legal because as long as you're multiplying both sides by the same amount, it's legal by the multiplication property of equality. Okay, next up, let's go to what else do we know? If you go back to the original drawing, on about, it seems like 99% of these problems, you're always going to use the segment addition postulate saying that this and this put together is equal to this. And since our reasoning here is segment addition postulate, we know that the only thing that we could state here is that I know that RS, not the actual place, the different distance from R to S plus the distance from S to T is going to have to equal the distance from R to T. That's the segment addition postulate. Now we're going to combine those two steps, step number 2 and step number 3, since both of these are equal to RT. And again, you can use transitive or you can use substitution. Substitution property of equality. We know that since they're both equal to RT, that 2 RS's and RS plus ST must be the same. Okay, now we go from there to RS equals ST. So what we've done from step number 4 to step number 5 is we've gotten rid of an RS on both sides. And how do we get rid of an RS? We take it away. We subtract it off. So if you take away an RS from two RSs, you're left with one. If you take away an RS from this side, you're left with just the ST. So that's going to be your subtraction property of equality. And then finally, in our last step, since RS is equal to ST, here's RS, here's ST, then that means that S has to be in the middle. If two things are equal, if RS and ST are equal, that means that S has to be in the middle because of the definition of a midpoint. So we know that S is the midpoint. And that is what we were trying to prove. Okay, number 9. Again, we're still given information here. We're given that M is the midpoint of LN, and they filled out half of the proof again. M is the midpoint of LN, which means this has to be the same as this. N is the midpoint of MO, which means that, since N is the midpoint, that means that this has to be the same as this. Since this is one tick mark, I'm going to go ahead and put one tick mark here because of that same transitive property. So we want to prove that LM is the same thing as NO, and we kind of already have because of that transitive property. So let's try to go through these steps. M is the midpoint because it's given. And since we know that M is the midpoint, that means that LM has to be the same as MN. And we've already gone through that. LM is the same as MN because of the definition of a midpoint. We're also given that N is the midpoint of MO. And we could have combined steps 1 and 3, and we can have also combined steps 2 and 4 because it's the exact same information. Since N is the midpoint of MO, that means that MN has to be the same length as NO, and again by that same definition of a midpoint. And now it's pretty easy from there. Since LM is the same as equal to MN, and MN is also equal to NO by the transitive property, we know that LM must be the same length as NO, which is technically pretty much what we're trying to prove. However, we've proved equality. We can now say that they are congruent, therefore by the definition of congruence. Okay, number 10. Okay, starting on number 10, we're going to do this whole proof ourselves. There's absolutely nothing given to us. So let's start out with the fact that y is the midpoint, and that is our given. And then asking ourselves, what do we know from there? Well, if y is the midpoint, again, where does that lead to? If this is the midpoint, then we know these are equal. So that means that xy is equal to yz because of that definition of a midpoint. And next up, we need to ask ourselves, well, what else do we know? Since it's a line segment, something else that I do know is I know that if you were to add x, y, and yz together, then you get the whole thing. And that's by the segment addition postulate. The only problem is that's pretty much all the information that's straightforward. So from that information, which is our plain and simple, we understand that. How can we get to this now? Well, I know that my final, what I'm trying to prove, only involves x, y's, and xz's. So I have my xy here and my xz here. Now I can get rid of this yz by replacing it now with that xy, and that in step 4, because of substitution, results in xy plus xy is equal to xz. And now we're on the right track, because I'm trying to prove that xy is half of xz, because now I can say that xy plus xy, well, that's 2 xy's, is equal to xz. And that's just simple simplification. Xy plus xy, well, that's 2 xy's. And again, all I did there was simplify. Okay, now to get from there to what I'm trying to prove, all I have to do is multiply both sides by a half. Half of 2 actually cancels that out, and half of xz, and that's what I'm trying to prove. So statement number 6, I can say that xy is equal to 1/2 of xz. And again, that makes sense. That follows that if 2 xy's is equal to, let me try to erase that, 2 xy's is equal to xz, that means that xy would be half of xz. But the actual technical reason behind that is I multiplied both sides by a half. The reason that's legal is the multiplication property of equality. And that is exactly what I'm trying to prove. Xy is half of xz. Number 11. We're given that AC and DF, which is the whole line segments, are congruent to each other. And we're also given that BC, which is this part, is congruent to DE. So let's go ahead and write down what we're given in our first step. And again, since we're dealing with congruence here, let's go ahead and switch those over to equalities, because most of our theorems and postulates and definitions involve equality. Okay, next up, again, I like to state anything that's obvious, and now we might use this, and there's a possibility we might erase this step. We might not need this, but I do know by the segment addition postulate that AB and BC add up to AC, and that DE and EF add up to DF. Okay, from here on out, there's several different ways of working this, and this is how I'm going to do it. Notice that AC and DF are the whole line segments, and they are equal to each other. These two lines are equal to each other. Well, since AB plus BC is equal to AC, and then the DE plus EF is DF, since they're equal to each other, that means that AB plus BC has to be equal to DE plus EF. That's the transitive property. Since they're both equal to equal things, then they're equal to each other. And again, by the transitive property. Now let's try to figure out, okay, how are we going to make that into what we're looking for? AB and EF are equal. So we're trying to say that this and this is equal to each other somehow. Well, I also want to put up or notice up here that BC and DE are the same thing. Well, what if we took away BC and DE from each side? Then we're left with what we're trying to prove. So let's take away, and again, we're subtracting the same amount from each side. It's like if this is 4, then this is 4. They're equal to each other by this statement right here. They're the same length. So let's take away these amounts from each side. And again, the reason that's legal is you can subtract the same amount from each side and it stays the same. That's the subtraction property of equality. And now pretty much we have what we were trying to prove. They're equal to each other, so therefore they're congruent, and that is what we were trying to prove. And again, by the definition of congruent, which we've used in nearly every proof. Actually, we have used it in every proof. Okay, number 12. Okay, number 12 says that AB and CD are the same length. And we want to prove that AC, which is this segment, is the same thing as this segment. Well, all we're doing is adding BC onto each line segment. So obviously, it must be the same still. So we're going to start out with our given. And from that given, again, we know that we deal with equality better than congruence, so let's go ahead and change it to equal. And now let's go into our segment addition. We know that AB, when combined with AC, is going to equal AC. And I'm going to go ahead and throw in the fact that CD, when combined with BC, would equal BD. Okay, now notice what I just wrote down. We're trying to prove that AC and BD are the same. This and this is the same. Well, notice something on the left side. These left sides are this exact same statement, the AB and the CD, just each of them have a BC added on to each other. So what I'm going to do in step number 4 is I'm going to take my step from 2, I'm going to take my AB, and I'm going to take my CD, and on both sides, I'm going to add the same amount. I'm going to add our BC. And that is legal by the addition property of equality. Now, let me go ahead and throw this out there that some textbooks or some programs are going to make you say, now BC is equal to itself. We're adding the same amount to both sides here. BC and BC is the same by that reflexive property of equality. They're the same, so that's the reason it's legal. So just be prepared that sometimes you might have to throw that in. But all I did was added equal amounts to both sides. And the reason I can do that is that addition property of equality. And now all I have to do is take my statement from step 3. Since AB plus BC is equal to AC, and since CD plus BC is equal to BD, I can replace this with AC is equal to BD by simply substituting that in now. So that's going to be your substitution property of equality. And now we're pretty much finished. AC is equal to BD, which means that they are congruent. And that would be by the definition of congruent.